All right, so today we're going to be doing day 23 in Advent of Code. The first part of this challenge is that we get a lot of different lines that have some letters on the left and some letters on the right, and they're separated by a dash. And what this is supposed to be is two different computers being connected to each other in a network map. And if we see that KH is connected to TC, then we have to say that KH is also connected to QP. So it means that these three computers are actually all connected together. So what we want to do first is to be able to take this input. As we see, this is the entire input that we get. It's two different computers connected to each other. We want to take this input and to make it into 3 lines long instead. So we take all the different 3 lines ones. So as we saw, we have these KH, TC, and QP and KH. This would be QP-KH-TC, and it doesn't matter what order we put them in, actually. They're the same thing, apparently. And once we do this and we put it in combinations of 3 instead, what they want us to do is to see how many of them contain a T, and we return the number, and that is what they want us to do. So the last part is quite simple, but actually making it into 3 instead of 2s takes a little bit of effort. So let's see. We have here all of the lines, which I got from the input file, and then we open it. And what we do is we build a graph. So for each line, I strip it and then I split it by the dash, because we can see that all of them have a dash in the middle, so that we can get the left side and then the right side and store it inside a connection, which is a list. And then we append to the connections the connection itself, so that we can have several connections. What we do after is that we build an adjacency list, and instead of explaining it, I'm gonna actually show it. So let's debug this really quick. And basically what we're doing here, we're just going to have, okay, the left side and the right side. So we're going to see that the connections variable is going to be just one number linked to another number, if this wants to actually run. So now if we look at connections, we see it here, and if we click it, we can see CR is linked to PY, WD to TP, and so on and so forth, and it should be the first ones. So if we go all the way, CR, PY, WD, VD to TP, and so on and so forth. But if we look over here, we made a graph, and right now it's empty, but we're going to slowly add stuff to it. So for A, B, and connections, and we saw that connections, the first thing would be CR and PY. So A and B would be CR and then PY. CR and PY. If A is not in the graph, what we do is we make it. So we could include the default dict, but we have to just create it in case it does not exist, and we create it as a set, because otherwise if we try to add something to it, it's going to give us an error because the key does not exist yet. But if you use default dict, you would not have this problem, but I just didn't want to have any libraries if I didn't have to. So we create A if it does not exist already, we create B if it does not exist already, and then at graph A we add B, and at graph B we add A. So we will see that we will have 2 different graphs in here. We have the graph CR, and in it we have PY, and then we have the graph PY, and in it we have CR. So if we go over this a bunch of times, if I just keep pressing, you will see that will keep being added, and at some point we will find one of the letters that's actually the same as one of those letters that we already have. So it's, for example, going to be VD is equal to TP and something else. But apparently it takes a while until the first occurrence of that happening. But I'm just going to keep running it. There we go. So now WD has a QS and a LP. And if we keep running this until the end, so if I take this stop point over here and I put it here, all of this is going to run until we reach this point here. So we will actually see how it would look like. And it seems that our input is not completely random, because somehow all of them have the exact same length as it looks like. And we store, as you can see, graph A and graph B, graph A of B and graph B of A, so that they're both pointing at each other. So we can see both ways what's going on. What we do after is we find all of the sets of 3 interconnected computers. So we look at every single node in the graph. So over here, we look at if we just press one step and I close the graph here, we will see that right now the node is going to be the first one, which is CR. And then we're going to get the neighbors of the graph node. So neighbors is going to be all of these things, which were the keys before. And then if we're going to look for N1 in neighbors, for N2 in neighbors, And right now they're going to be the same. So if we go step by step, and they're both the same. So this is not going to go through because they shouldn't be the same. And what we're trying to do is to see, okay, are they not the same? And if they're not the same, then is N2 in the graph N1, meaning that they are connected to each other. So if we had just A, B, and C, so forget this one, what we were looking at is A and B connected, and then what we're looking now at is N2 and N1. So we're looking if B and C is connected. So if this is true, then it means that they are all three connected. So then great, add it to the nodes. So let's see if this actually happens. In the first case it didn't, but now that it's A and AB, maybe A and AB have a graph somewhere where they are connected, and let's see if it's true. It seems like it is, and if it is, then we add it to the 3 nodes. So if we go one step and we close this and we go to 3 nodes, we can see we have A, B, C, R, H. Then if we let all of this run, we will see all of the 3 nodes that we actually get. So let's see how many 3 nodes we actually got. Seems to be quite a bit. I'm not going to be scrolling all that way. Then what we do is with it, we filter the 3 nodes to include at least one of the computer that starts with T. So this part is quite simple. We just look for every single place and we see, okay, does it start with T in any location? So KT is not valid because it ends with a T. TH is valid, but not in neighbors. We're going to be looking at in the 3 models. So this one won't be valid, not valid, not valid, and at some point one of them will have a T in the beginning. And we find it, then we filter it, and we don't really have to filter it. We could just make a counter and just do +1 whenever we find one, but I just like to do it like this because we can just store all of the correct ones actually and then print them as well. So if I go here and I remove this one so I can continue to the end, then we will see that the filtered ones, if we close the non-filtered ones, where's the filtered ones? Filtered 3 nodes. So all of them contain a T somewhere. TQ here, TV here, TP here, TD here. And then what we want to do is just to print the length. So what size this list is right now, or tuple. And when we print it, we get 1344. And that should be the correct answer. 1344, nice. So that was part 1 with debugging. Now for part 2, what we have to do is explain what the problem is first. So right now, what we have to find out is what is the biggest sort of network that there is from our given input. So what classifies as a valid network is if we have A, B, C, and D, is not just being able to traverse to all of them. So if we go from B to A, and then we go to C, and then we go to D, so okay, congratulations, you can get from computer B all the way to D. That's great, but that's not what they classify as an actual network. So what they want is to have every single node reach each other. So right now, if we have A to C and C to A, it's the same thing, then this one is classified as an actual node, as an actual network. Then if we want to add B, it's not enough that we connect A to B and B to A. What we also have to do is to connect B to C. So all of the nodes in the network have to point to each other as well. So if we add D, we don't only connect it to B, we also have to connect it to C, we also have to connect it to A. And if we add E in here, we don't only connect it to B, we connect it to D, C, and A. And you can see the more letters that we add, the more connections we're gonna have to use. So it's gonna get ridiculous at some point. So that's what they classify as a actual network. And to be able to enter the LAN party, we need a password. So once we find the biggest network that we can possibly find, what we have to do is alphabetically sort it, separate it by commas, and then give it as the actual answer. And this was my answer. So let's see if we can get to it again. So we open the lines again, we build the connections as we've done before, we build the adjacency list, and we do it the exact same way as before. Now we have a helper function, but let's first look down here. So what we do is we go through every node in the graph, and we find all of the networks, and we go through all of the nodes, and we give it to the search function, which is this function right here. And then what we do after, since the search function does a bunch of calculations, it looks at the visited networks and it adds a bunch of keys to it, So what we want to do is to find, okay, which visited networks has the most elements. So by saying max visited networks, and how do we know what we're looking, like what is the max thing that we're looking for? Well, we're looking for the key and the length of how many keys there are. If we said that, if we said something else, like the actual value of the key or something else, then that's what it would return as max. But we want to know how many keys there were and get the max one. And that is the largest network, which we will sort so that we can join it with commas, because they want it alphabetically. And sorting it, if it's not an integer, if it's a string, it does it by default alphabetically. So if we look at the search function, it takes the node and the actual values. So the node and the network, we can say. Then we make a key with the sorted network as a tuple. And if the key is already in the visited networks, then there is no point to actually check it again, because we've already found it to be there. But this shouldn't actually happen if this input is actually efficient. It shouldn't give us like redundant data, basically. So here we just return, we do nothing. But if it is not the case, if it's not already in the visited networks, we add it, of course. And we check if for every neighbor in the graph node, I'm gonna try to debug as well to show it a little bit, but it might take a second to start. So for every neighbor in the graph node, if the neighbor is in the network, we also continue, because we don't want any neighbor to also be already in the network, since we're trying to add it to the network. Oh shit. So let's go inside here. So if we continued this part as well, and we actually got to here, we check if not all the neighbors are in the graph of the other one for other in network. So it means that if all of them are not connected, then we also continue. So somehow, if there's one tiny little thing missing, so if this one was missing, if this one was red, B to A, and we had this many nodes, and all of them connect to each other one by one, but if there's one of them that's missing, we've just done this in one line here, so we check all of them. If it's not the case, then we continue. So all of them have to be connected. But if they are all connected, it's not going to continue, and it's going to go into here, which is to search the same neighbor, or not the same neighbor, whatever neighbor we're at from the for loop, and we're going to concatenate or do a union of the network and the neighbors. And this is a union operator in Python. So concatenation is if you imagine two different strings of or digits 1 and 1, we would get 11. If we have S and T separately in quotes, then what you would get is ST together in a single quote. And what we're doing here is we're taking two different lists that are different and have different values in them, and we unite the actual values that are in them. So if we have a list that has one element and a list that has 100 elements, then it's going to combine them, and we're going to get a list with 101 elements that are 100 from here and 1 from here. So it's going to combine two lists. That is what this operator does. Then we're going to search again and again and again until we've gone through all of the neighbors in the graph node and made sure that all of them actually connect to each other. And all the while we added to the visited networks, which we check for, and we see which one was actually the biggest. So if we go over here and we continue until we get here, whoops, take this away so it can run all the way until down here. It might take a second. So it will stop at this line, but will not actually run this line until I tell it to continue. And then we can see what the visited networks actually are when it gets there. And then we get the password and we print it. But it's going to take a second, of course. While it's running, let's talk about the time complexity of part 1. So we have making the graph and making sure that we make it into 3 instead of 2s as we got it from the input, and then actually finding all the t's, which isn't that complicated. So the time complexity is it looks a bit weird, but it's n plus n times m squared plus k. But since this is not significant, the most significant value, then we can just say that it's n times m squared. And m is the average number of neighbors per node. And we saw that the average number of neighbors was about, I don't know, 10 to 20 maybe. So this could be times 100 in this specific input case, and assuming that all the different inputs that the advent of code gives us are kind of the same, just different numbers, we could kind of get rid of this, but I kept it anyways. And then we have plus k as well, because we have a certain amount of triads that we have to calculate and compute the t for. And for the space complexity, it's going to be n times m plus k, which isn't that bad, and it's expected. So for the time complexity of part 2, it's a little bit worse, because we have the search function, which is n times 2 to the power of n. And this is because the more we add, so now if we have a g, then this one not only has to check, okay, are all of these connected to each other, but also the new one, is this one connected to all the previous ones? So it gets exponentially worse the more that we add to a certain network. So it's 2 to the power of n, and that is how many lines we have in the input for just finding the largest network. So the actual total is n times 2 to the power of n, which is pretty bad, not for an actual solution, because it's difficult to actually get a better solution than this. I don't know how you would do it, but compared to the first part, this takes a lot longer, as you can see. So I don't even know if it's going to actually load the compiler. It's going to take way too long. So I'm just going to run it normally. It should still take quite a bit. And of course, the time complexity as well is n times m, which is similar to what we had in the beginning, but we also had plus k, which was the number of triads. But in this case right now, what we have is plus 2 to the power of n, which is being able to find the largest network. And we have to store all of that information of the network. So that is why it's added here in the space complexity. So we got the answer here, AB something something ending with UH. And it seems like it's correct. So that was Advent of Code Day 23. If you guys want to join the leaderboard, I'll be leaving the codes in the description. And thank you for watching. Happy holidays, and see you tomorrow.